all, do we understand that what does this S times indicator function of B means actually? Okay, let's try to make sense of it. So it's like restricting the domain of the function. So before S is defined on whole X to the, you know, maybe R, okay, R or 0 to infinity or whatever, you know, the whole domain is. But what would be S multiplied by indicator function of B? So if I operate this on X, it means that I have to take, okay,
0 or SI can answer.
so it's going to give you not 0
S of X.
So it's going to S of X multiplied by the indicator function of X actually. Okay? So you're going to get what? So you're going to get S of X
If X is in B,
X is in B.
0 if X is not in B.
So it's a kind of a cutoff function actually that you saw in function analysis. So when you multiply the indicator function with some function, you don't want to see the function on the whole space, but you want to see the function on a particular set actually. Or a particular
Turn off.
So you have to keep this thing in hand. Okay? Okay. So here's a quick preparation for the proof. Okay. So what we have B, so the B is some measurable set. Okay. And S is a simple function. So if it is a simple function, then S can be written as the sum actually, I equal to 1 to n Si and indicator function of AIs actually. Okay? And what are AIs? So we are A1, A2 and up to AN. These all are elements from the sigma-algebra and they are mutually disjoint actually. So they are mutually disjoint. Okay? And since S is non-negative, also all of these small SI's are non-negative numbers actually, because S is a non-negative number. So obviously if S is defined in the terms of SI, so it must be non-negative as well. Okay? Now, essentially you have to see what would be the domain of this function, SIB. So it,
Whole X.
no. Okay, obviously it's going to be whole X, but if you want to see this as a simple function, you have to tell that, okay, what are the pieces on which, okay, what are the sets on which this treats as, or this works as a simple function. So then essentially you have to do what? Okay, S is defined through these AIs. So that part of AIs which lie in B, okay, is going to be the, essentially, because on that, you know, the both functions work. So, you know, obviously S is going to work and indicator function of B both is going to work actually, okay? So if I take CI's, some setting, take CI as AI intersection B actually, okay? Take CI as AI intersection B, okay? Where I is 1 to up to n, okay? And I can take Cn plus 1 for example as x minus what? The union of AIs, I equal to 1 to n, then x minus b, okay? So everything else x minus b. So Cn is what? The intersection. So here the function is going to have some value, this product is going to have some value, but here the function is not going to have any value, so it's going to be 0 actually. Okay? Because the indicator function outside B is 0. So obviously making sense? Yes. Okay. I'm also assuming, so it's just a, so see, it's just a prep actually. So these are the small things that you have to keep in head if you want to, prove this result. So it's just a small prep. Next, next I am saying that I want to see the indicator function SIB as a sum. Okay? From where to where? From I equal to 1 to n plus 1. Okay? And it would be the product of Ri's, which I am going to define soon, multiplied by the indicator function of Ci's. So give me a guess for Ri's, where Ri's are what?
Sir, won't say remain
So,
same नहीं होंगे वो.
yes. So Ri is Si. Okay. When for I equal to 1 to n, and Ri is 0.
For n plus
N
1.
plus 1 actually. I is okay, so on and so forth. So it's precisely the same thing. Okay. So I just want to keep the interpretation. Why I'm doing all that? Because now I can write this abstract integral very concretely. So if I have this guy concretely related in this manner, then what would be the nu of b actually? So the nu of b is going to be the sum I equal to 1 to n plus 1 Ri and the mu of Ci. Okay, so this is going to be the case. So now I have an explicit expression, and then now ask what you want to ask actually. Okay, so the first thing, the first property, let's take B to be the empty set. So if you take the B to be empty set, what you're going to get? The nu of the empty set is going to be the nu of Ci, but in this case all Ci's are going to be empty set because you are intersecting AI with some empty sets, and their measures, because mu is a measure, is going to give you 0, so this would be 0. Okay. Now let's go for the countable additivity. Okay. So imagine I have bi's from our sigma-algebra, and I want to union the bi's. I equal to 1 to infinity bi, and I'm giving this whole set a name b. Okay, so I'm giving it a name b. It's fine actually. And now I want to operate nu on this b, and I want to see. Let's see what we get. Okay, so help me out with the calculation. So, okay, I have a lot of space there as well. So the nu of b is going to be what? Is going to be, obviously I equal to 1 to n sum of Si, okay, no, maybe Ri, whatever, times mu of Ai intersection B.
सर CI की नहीं लिख सकते कलेक्शन में.
क्या मतलब?
डोमेन वाले होने चाहिए ना.
डोमेन ही लिखेंगे ना. So that's
So
CI.
ठीक है.
So that's CI. Okay, that's CI.
ठीक है.
Now, but this B now is a union actually. Okay, so now B is a union. Then I can apply the distributive law. Okay, so it's going to be what? It's going to be I equal to 1 to n. Okay, let me write it here. So it's going to be I equal to 1 to n or n plus 1 or n or whatever. Okay, times Si. Okay, Si and mu of I. How can I write it? So AI intersection. Okay, let's not use the same index. Let's put a j here. Okay, let's put the index j. then I can write this as j equal to 1 to infinity of AI intersection bj. Agree?
सही है
Okay. Now mu is additive on this joint sets actually. Okay. So what will be this? So I equal to 1 to n si, and you're gonna have j equal to 1 to infinity and mu of AI intersection bj. Agreed? So you have this. And then this would be I equal to 1 to n, j equal to 1 to infinity. I can combine this sum, I can take this number and multiply with each term here, so that I can have this si mu of AI intersection
BJ.
bj. Okay, I want to do the rest of the calculations on the other side, but if you think about it, I can do another thing. Can I swap these actually? I don't see a trouble actually. So j equal to 1 to infinity, I equal to 1 to n, sometimes must go hundua. So you have to be careful. Okay? So, yes. So I'm doing what? So it's like I'm saying that the finite sum of these infinite sums is same as the infinite sums of the finite sums, something. So Si and mu of AI intersection bj's. Agree? Okay, so let me write it here. So the final thing that I'm going to get is going to be j equal to 1 to infinity. Okay? So tell me that what would be this last term basically. So how can I write this finite sum as actually?
Integration.
So this is nothing, but this is nu of bj, if you see. Okay? So in your definition of nu, just replace b by bj. So you have this actually. Okay?
Sir, second last you third last or second last follow correct? Second step or third step?
This one. So I'm saying that I have this infinite sum.
Yes, sir.
And I'm taking this number and multiplying with this infinite sum. And so so it's like multiplying a series by a number is well defined actually. So we know what is the meaning of multiplying a series by a number. So it's like this sum is there, I'm taking this number and multiplying this with the whole series, so this is going to get inside.
That's fine, sir. Distribute or
but we have a justification, what do you call, from real analysis, because we know that you can sum two series and you can multiply them with a scalar and so on and so forth. Okay? So you get nu of bj. And its pronunciation is nu. It's not a mu, so mu is different. So it's nu of bj. But bj's are all disjoint actually. So okay, just for a moment. Yes. Okay. So this is what that we wanted to prove. So this completes the proof. So what did we need to do? We started with nu of the union of bj's, and we reached to the the sum of all those bj's.
सर वो जो आप मतलब पहली लाइन है उससे जो नेक्स्ट स्टेप में आए उसमें आपने म्यू की मेजर की प्रॉपर्टी यूज की है ना म्यू
yes, yeah, we have used the additivity of this. We have used the additivity. Okay. So you have to think that why they are disjoint.
हाँ सही है सर.
Why each AI Bj is, so why A1 B1 is different from A2 B2 or something like that. Okay? You have to think about it. And I haven't justified it. And that's it. So this simply completes the proof. Alright? I think that's it for today. what we did essentially